Hello everyone. Today topics of discussion are binary search tree, operations on binary search tree, expression tree, and conversion of a general tree to binary tree. Let us start with what is the binary search tree. Binary search tree is one of the important data structure in computer science. It is also called an ordered binary tree or sorted binary tree. The in-order traversal of a binary search tree gives a sorted list. A binary search tree is a binary tree which has three properties. First, all nodes of a left subtree are less than the root node, and all nodes of a right subtree are greater than the root node. Third property, the left subtree and the right subtree must be a binary search tree. That is, they have property 1 and property 2. In addition to this, there must be no duplicate nodes in a binary search tree. Next, some important points of a binary search tree. The binary tree provides efficient searching of an element because at each step we will get an idea about which subtree contains the desired element. It is also considered an efficient data structure in compared to linked list and array, because the average running time to search an element in a binary search tree is big O of log n base 2, and in worst case running time to search an element is big O of n. But average running time to search an element in a sorted array is big O of log n base 2, but it is expensive to insert and delete elements. However, binary search tree speed up the insertion and deletion operations as compared to that in array and linked list. Okay. Next, this figure depicts a binary search tree. Why? Here you can see that all nodes of a left subtree of a root node are lesser than the root node, that is 20, and all nodes of a right subtree are greater than the root node, that is 20. And also you can see the left child of a root node 15 of the left subtree of 20, okay, that is a 10 is less than the root node 15, and the right child, that is 18, have the value greater than 15. In the same way, you can see the left child of 40 has less value and the right child of 40 has a greater value. Therefore, we can say that this is the example of a binary search tree. Next point. How will we define or declare a node of a binary search tree? In a binary search tree, the node of in a binary search tree contains three information. First is the data, next is a pointer to the left child, and next is a pointer to the right child. And how we will declare this in a C language? With the help of the structure facility. Here you can see on the slide struct node. followed by the left braces. Int data is the information. And node star left is a left pointer, and node star right is a right pointer, means a pointer to the right child, and followed by the right parenthesis and followed by the colon. So this way we will define a node of a binary search tree in a C language. Next, suppose we want to draw a binary search tree for a given data elements. So how will we build a binary search tree for a given set of elements? Suppose the elements are 55, 35, 10, 60, 30, 80, 55. Okay, in the place of 55, you can think the other number, suppose the 52. Okay, now step 1. Take the first element item, that is a 55, and at this time there is no element in a binary search tree. Okay, now this 55 becomes the root of a binary search tree. Okay, so 55 will become a root of the binary search tree. Take the next element, and next element is 35. Okay, now compare this 35 to the root of the binary search tree, that is a 55. Here we can see that 35 is less than 55. Therefore, we attach 35 as a left child to the root node 55. Okay, so 35 will become the left child of 55. Okay, now take the next element. The next element is 10. Okay, now we compare this 10 again with the root node. So 10 is less than 55. Okay, now again we compare this 10 to the left child of 55, that is 35. And here we can see 10 is less than 35. Therefore, we will attach this 10 as a left child of the node 35. Okay, take the next item. Suppose next item is 60. Okay, again we compare this 60 to the root node. A root node is 55. At this time we can see the 60 is greater than the root node 55. Therefore, we attach this 60 as the right child of the root node 55. Next element is 30. Okay, take the next element, and next element is 30. Compare this 30 with the root node 55. It is less than 55. Therefore, we will go in the left subtree. Again compare this 30 to 35. Here we will see 30 is less than 35. Then we will again go to the left subtree of 35. Okay, now we can see, compare this 30 to 10, and here we will see that 30 is greater than 10. Therefore, we will attach this 30 as the right child of node 10. Okay, next is suppose 80. Again we will compare this 80 to the root node. 80 is greater than 55. Therefore, we will go in the right subtree. Again we will compare this 80 with 60. Here we will see the 80 is greater than 60. Again we will go in the right subtree. Okay, and attach this 80 as a right child of node 60, because 80 is greater than 60. Take the next element, and here we can see the next element is 57. Again we will compare 57 with 55. 57 is greater than 55. Therefore, we will go in the right subtree. Again, compare this 57 with to the root node of right subtree of 55, that is 60. And here we will see 57 is less than 60. Therefore, we will attach this 57 as the left child of the node 60. This way, we will draw a binary search tree for a given data elements. Okay. Now, next topic, operations on binary search tree. Searching for a node, inserting a new node in a binary search tree, deleting a node, determining the height of a binary search tree, determining the number of nodes in a binary search tree, determining the number of internal nodes, number of external nodes, finding the mirror image, deleting a binary search tree, and finding the smallest or you can and largest node in a binary search tree. We start with the first, searching for a node. Let us first see the algorithm. Search node. The name of algorithm is a search node. It has two parameters. First is the tree, and next is the searched item, S item. Step first. If tree is equal, what we will do in this case? We simply give a message empty tree and return tree. Means okay. Next, if tree data is equal to S item, what we will do? Simply we give a message item found and return tree. Return to the calling place of search node function. Okay. Else, if the item is not found at the root node, what will we do? We compare the search item with the root node. Else, if such item is less than tree data, what we will do? Here you can see we will again call the search node function, a procedure algorithm with parameters tree left. At this time, we will follow the left subtree of the root node, means the tree left. And next is the search item. Else, such item is greater than tree data. What we will do? We will go to the right subtree of the root node. Means we will call the function or procedure, or you can say the algorithm search node with the parameter at this time tree right. And you can observe that this tree right is a pointer to the right child of the root node, and tree right in the algorithm becomes the root node. Tree right comma search item. And next step, stop. Let us take an example how this algorithm will work. Suppose we want to search item 18. So first, we always start with the root node. Compare this 18 with the 20. Here we can see 18 is less than 20. Then we will call the searching process recursively tree left. Okay, in the algorithm you can see if the search item is less than the root node, we will follow the left subtree of the root node. Means tree left. Tree left now point to the node 15. Compare this 18 with the node 15. Here we can see 18 is greater than 15. Okay. Now we will call the procedure or function with parameters tree right and search item. And tree right now becomes a root node. Now we compare 18 to the root node 18, and here match is found. Such item is equal to tree data, means item found. Is that clear? Next, suppose item to be searched is 60. Again compare 60 with 20. 60 is greater than 20. We will follow the right path and we will searching process with two parameter, call the searching process with two parameter. One is the tree right and the search item is 60. Now tree right now becomes a root. Now compare this 40, here the root is 40. So 40 is compared with 60. And here you can see the 60 is greater than 40. Now we will again recursively call the process tree right, comma 60. Now tree right means the node 50. Now we compare 50 with 60. And we will see 60 is greater than 50. We will follow to the right subtree of 50. And here you can see tree right at this time, tree right contains the value null. What it means? Tree right is equal to null. What it means? It means that item does not exist in the binary search tree. Means this item is not in a binary search tree. Okay, so we simply gives a message item not found. Okay. Next, suppose we want to insert a new node in a binary search tree. Let us see the algorithm. Insert a node with again a two parameter. First is the tree pointer and next is the item to be inserted in a binary search tree. If tree is equal to null, means suppose we are going to add the first element in a tree. At that time, tree is equal to null. What we will do? First step, allocate memory for tree node. Next step, set tree data is equal to item to be inserted into a binary search tree. Next step, tree left is equal to null, tree right is equal to null, and return tree. We have finished our work. Suppose we are going to add the first element in a binary search tree. Okay, that node will become a root node of the binary search tree. If tree is not equal to null, what we will do? Means the binary search tree has at least one item, or you can say the node. What will we do in this case? If item is less than tree data, what we will do? We call the insert node algorithm recursively with parameter tree left, because at this time we want to insert the new item in the left of the root node, comma item. Else tree right equal insert node tree right, comma item. If the inserted item is greater than the root node, what we will do? We will go in the to insert the item in the right subtree of the root node. Okay. Next, end if. Next step, stop the algorithm. Suppose we want to insert the node 35 in existing tree, binary search tree. Here you can see the binary search tree contains the nodes 20, 15, 10, 18, 40, 30, 50. And here we want to add the item 35. How will we add this 35? First, we will compare this 35 with the tree data. Okay, 35 is greater than 20. So we will call the insert node function with parameter tree right comma item. Tree right now points to the 40. Again, we will compare this 40 to 35. Here we will see that 35 is less than 40. Now we will again call the insert node function with parameter tree left. Now tree left point to the 30. Again we will compare 30 to 35. And here we will see 35 is greater than 30. Then we will again call the insert node parameter function with parameters tree right comma 35. Now you can see tree right is null. Okay, and this tree right null becomes the value of tree. And when the, here you can see, when the tree is equal to null, we simply insert the item. Allocate memory for tree node. Set tree data. Here data is 35. Tree 35 is equal to tree data is equal to item. Item is here, can see 35. And we set tree left is equal to null and tree right equal to null and return tree. We have finished the inserting this 35 into a existing binary search tree. Here you can see we set left and right child of this 35 to null. Okay. Next, deleting a node from a binary search tree. Here we can classify the deletion activity in 3 cases. Case first, deleting a node that has no children. Next case, deleting a node with 1 child. Next, deleting a node with 2 children. One by one, we will see these 3 cases. Suppose, case first, no children, item to be deleted. Okay. And suppose we want to delete the node 35. Is it clear? And the 35 has no child node. Okay. We want to delete the node 35, and you can see that 35 has no child. Okay. Again, we compare this 35 to 20. Since 35 is greater than 20, we call the delete process recursively with parameter tree right comma 35. Tree right now points 40. Again, compare this to 35. Okay, and call the delete process with tree left comma 35. And what is the tree left? Tree left now point the 30. Now compare this 30 to 35. Here we see 35 is greater than 30. We call the delete process with parameters tree right comma 35. And tree right now points to 35. Is it clear? Now, here we can see the tree data is equal to 35. Means item, the deleted item to be deleted exists in a tree. Okay. Now suppose a pointer is PTR for time being, let us assume. Now PTR is pointing to the 35. What we will do at this process? We simply set temp is equal to PTR. Okay. set right node of PTR parent. Right node of PTR parent means 30 to null. Now this 35 becomes the null value and free the temp, means that node 35 is deleted from the binary search tree. Next case, suppose we want to delete the node 30, and here you can see the 35, the node 30 has one child, the right child. We will repeat the same process, and suppose PTR is a pointer which points to the node 30. Is it clear? Now what we will do in this case, if PTR left, here you can see the PTR left is equal to null, means the left child of this 30 is null. What we will do, we set temp is equal to PTR. Next step, set left node of PTR. Left node of PTR parent. Left node of PTR parent means 40. Node 40 points to the PTR right. What is the PTR? PTR is the 30 and PTR right is 35. And the parent of the PTR is 40. So 40 left now becomes to a PTR right means 35. Means the 40 node 40 points the 35. Okay. And now we are free to delete this node 30. Is clear? Okay. Next, the child to be, the node to be deleted has the value 30. Okay. Now in this case you can see the deleted node has the left child. What we will do in this case, we simply set PTR right is equal to, if PTR right is equal to null, set temp is equal to PTR, and set again left node of PTR parent means 40. Left node of PTR parent means the left of the 40 now points to PTR left means 25. Okay. And now we are free to delete the node 30. Is it clear? Third case. Suppose item to be deleted is 40. Again, we repeat the same process. Compare this 40 to 20. Okay. 40 is greater than 20, root node 20. We call the deletion process with parameters tree right, comma 40. Tree right means now points to the 40. Here we can see that tree data 40 is equal to the item to be deleted 40. Okay. And here you can see the deleted item, the item which we want to delete has two children, 30 and 50. What will we do in this case? Here the target node is 40, is replaced with the largest value in its left subtree. And what is the largest value in the left subtree of the target node 40? You can see the 35. Replace this 40 with this largest node in the left subtree of 40. Now 40 becomes to 35. Okay. And then node is deleted as before case 2. Now what is the case 2? Here you can see the 40, now 35 becomes a node 40, and 40 has only a single left child, and we have a technique to delete a node which has a single child node. Okay. And now we delete the node 35, that is now becomes a node 40. So this way we can delete a node which has two children node. Okay. Here you can see this is the algorithm delete node with parameter tree and next is the item. If tree is equal to null, item not found, we simply give some message item not found and return tree. If item is less than tree data, what we will do? Tree left, we recursively call the delete node with parameter at this time tree left comma item. Else, if item is greater than tree data, we set tree right is equal to delete node tree right comma item. Is it clear? Now, next else. Not the both cases. What will you do in this case? If item is equal to tree data, else means here else means the control comes at this place when the deleted item, the item which we want to delete is equal to the tree data, means the control goes to the target node. We reach the target node. What will we do in this case? We have already discussed these things previous videos. We simply said temp is equal to tree, where we have written the PTR, and here is the tree. So temp is equal to tree. If tree left is equal to null, only one child or no child, tree equal tree right and return tree. Else, if tree right is equal to null, what we will do? We simply said tree left, return tree ending. Next case, if tree left and tree right means the item, the node which we want to delete has two children node. In that case, we have already seen the algorithm replace with in order predecessor. That is the maximum value in its left subtree. Okay. Now we find the maximum value temp is equal to largest node tree left. Here you can say the largest node is a function. We will see later in this video how will we define a largest node in a given tree. We will see this function. Okay. Next is set tree data is equal to temp data. Next, set tree left is equal to delete tree left comma temp data. And if of this if statement, and this is end if is the previous if statement, return tree, and next is the stop. Next algorithm, suppose we want to determine the height of a binary search tree. Here you can observe that we have written all algorithms in a recursive manner. Why? Because I have already told you a recursive definition of a tree. Since it is very easy to define a tree in a recursive manner, if a problem is defined in a natural way, in a recursive manner, then it is very easy to write a recursive algorithms. Okay. Now, come to the point. Suppose we want to determine the height of binary search tree. Step 1. If tree is equal to null, what is the height of the tree? 0, return 0, else. Set left height is equal to what? HBST. We again call a recursive function with parameter left, tree left. Okay. Next, set right height is equal to HBST, the name of the functions, tree right. And if length left height is greater than the right height, we return left height plus 1. Otherwise, we return right height plus 1. Okay. Next step is the stop. Next is the, suppose we want to determine the number of nodes in the binary search tree. Again, it is very easy to write a a recursive function for this problem. If tree is equal to null, return 0. Otherwise, return total number of Tn is the total number of nodes. Tn tree left plus Tn tree right. Here you can see the recursive function plus 1. Next, and if next step is a stop. Now let us take one example. Suppose we want to find out the number of nodes in a binary search tree. What is the formula to determine? You can say number of nodes in a, how will we write a formula in a recursive manner? Number of nodes in a left subtree plus number of nodes in the right subtree plus 1 gives the number of nodes in a binary search tree. And suppose you want to determine the height of a binary search tree. The height, how will we determine? The height of the left, how will we write a recursive formula? Height of the left subtree, next height of the right subtree. Determine the height of the left subtree and height of the right subtree. If height of the left subtree is greater than the height of the right subtree, what we will do? We simply add 1 to the height of the left subtree. If the height of the right subtree is greater than the height of the left subtree in a recursive manner, please keep this point in your mind. We simply write the height of the right subtree plus 1 gives the height of the what? Height of the binary search tree. Let us see. In this way, you can determine the height of a binary search. Suppose, let us take one problem you can understand. How will we determine the number of nodes in a binary search tree? How will we write a formula? You can say total number of nodes in the left subtree plus total number of nodes in the right subtree and plus 1. Plus 1 is the root node. Gives the total number of nodes in a binary search tree. Okay. Here you have seen, if tree is equal to null, we simply return 0, means number of nodes in the tree 0. As total number of nodes is equal to tree left plus total number of nodes in the tree right plus 1. It gives the total number of nodes in a binary search tree. Okay. Let us see here how we will determine the total numbers of nodes in a binary search tree. Let us see in details. We call the tree nodes function with parameter tree. Okay. Now, here you can see tree is not empty. And if tree is not empty, what we will do? We call the function with tree left, total number of Tn, tree left plus Tn, tree right plus 1. Okay. So let us see. Tn tree left. Okay. And what is the tree left? Tree left is the node 15. Here you can see tree node is left 15 and tree right is a node 40. Is it clear? Now, so Tn tree left in a bracket I have written is the 15 plus tree right for node 40. Okay, plus 1. Okay. Now, here you can see that Tn is a recursive. We are again calling the same function with tree left. And what is the tree left? 15. Now this 15 becomes the root of the left subtree of the root node. Here you can see tree left of node 15. What is the tree left of node 15? You can see here 10. So we are calling the function Tn with tree left means node 10. Again, we call the function. Here you can see the green is a suspended activity. here what you can see. Tn is divided into three parts: Tn tree left plus Tn tree right plus 1. And Tn is a recursive function, and here the Tn tree right plus 1. These are the two suspended activities, and these two information goes on the stack. Keep in your mind. Okay. Now control calls the function tree left, and tree left, Tn tree left means node 10. Again, a recursive function Tn tree left plus, here you can see the tree right, Tn tree right. And what is the Tn tree right? Node 18 and plus 1. 18 tree right plus 1, these are the suspended activity. Again, we call the function Tn tree left. And here you can see the left child of 10 is empty. Therefore, we call the function Tn tree left. And you can see at this time, the function returns the value 0. 0 is returned to Tn tree left. And okay, now most suspended activity is the, now here you can see Tn tree right. Now the system calls this function. Again, tree right is empty. The system gets a value 0. Okay. So 0 plus 1 is returned to, you can see at this place, tree left. Next suspended activity, this receives the value 1. Now the system calls this function Tn tree right plus 1. Now you can see here details of given this. The left subtree of node 18 is 0. Okay. So tree left plus tree right plus 1. So left subtree is 0. The system receives the value 0. And again the right subtree is 0. System receives the value 0 plus 1 means Tn tree right receives the value 1. Okay. Now here you can see. Now Tn, the nodes 15, at the place node 15, the recursive function will get a value 1 plus 1 plus 1 means 3 value. Okay. Now before this, what is the suspended activity? Tn tree right means node 40 plus 1. So here you can see node 15, at the place of node 15, the recursive function tree left gets a value 3. Okay. And now let us see what will be value returned by the recursive function Tn tree right. Here the details are given in this slide. You can see the node 40, in the place of node 14, the recursive function Tn tree right gets the value 5. Now here you can see, now the calling function received the value 3 plus 5 and plus 1 means total value is 9. And here you can see this binary search tree has 9 nodes. Okay. So this way a system determines the value of total number of nodes in a binary search with the help of a recursive functions. Okay. In the same way, we can write a function for a function to determine the number of internal nodes in the binary search tree. The name of the function is the total internal nodes. If tree is equal to null, we return 0. Okay. And here we want to determine the total number of internal nodes in a binary search tree. Okay. Now, if tree is equal to null, return 0. Else, tree left is equal to null and tree right is equal to null. What it means? This is the tree left and tree right is equal to node. Means the external node. Okay, leaves node. If leaves node, we will return the value 0. Here you can see. Here we want to determine the internal nodes. And this condition gives the leaves node. Tree left is equal to null and tree right is equal to null. What we will do in this case, if a node has left and right child is equal to 0, means that node is a leaf node. Else, we will return the total internal nodes function, tree left plus total internal nodes, tree right plus 1. Okay. And suppose we want to determine the number of external nodes. Here you can see the both total external nodes function and total internal nodes function both are the same with one difference. Here you can see we want to determine the external nodes. External nodes means we want to determine the leaves nodes in a binary search tree. The difference at this place, if the tree left is equal to null and tree right is equal to null, we will return the value 1. Means we have reached the external nodes. If we reach the external nodes, if we will able to determine the external nodes, if control goes to the external nodes, we simply returns a value 1. Else, return total external nodes tree left plus total external nodes tree right plus 1. Okay. Next is we want to determine a mirror image of a binary search tree. And how will we make a mirror image of binary search tree? We simply switch the left subtree to the right subtree and right subtree to the left subtree. And we will get a mirror image of binary search tree in a recursive manner. Again, in a recursive manner. Here in the left hand side of the left side of figure gives a binary search tree, and we want to make a mirror image of this subtree. Simply what we will do, we simply change the left subtree to the right subtree and right subtree to the left subtree. Now you can see the node 15 goes in the right direction, becomes the right child, and the right subtree becomes the left subtree. You can see in the figure. Okay. Next step. Again, we will change the left subtree of node 40 and right subtree of node 40. Change these two nodes. We will get the mirror image of binary search tree. Means the node 30, the left child becomes the right child and right child becomes the left child. Okay, so this way we will get the mirror image of binary search tree in a recursive manner. Okay, and the function is, if tree is not equal to null, mirror image tree left. Next, mirror image tree right. Set temp is equal to tree left. Set tree left is equal to tree right, and set tree right is equal to temp. Step second, stop. Here you can see we have again written a recursive function. Suppose we want to delete entire binary search tree. If tree is not equal to null, what we will do? Delete tree left. Next, delete tree right, free tree, and if next step, stop. Next, suppose we want to find largest node in binary search tree. Simple technique. If tree is equal to null or tree right is equal to null, we simply return tree. Else, return largest node tree right. And the next step, stop. Next, find the smallest node. Simple technique. Step 1, if tree is equal to null or tree left is equal to null, we simply return tree. And what here, tree is the root node. Okay, else return smallest node tree left. And okay. The last topic is the expression tree. What is the expression tree? Expression tree is the strictly binary tree and it can be used to represent an algebraic expression. Okay, expression tree contains operands and binary operator. Non-leaf node represents operator and leaf node represents operand. Okay. Next point. The pre-ordered traversal of expression tree gives a prefix expression. In-order traversal of expression tree gives the infix, and post-order traversal gives a postfix expression. How to make an expression tree manually? Suppose we want to make an expression tree from a given expression. So how will we make an expression tree? Keep 2 points in your mind. Use the operator precedence rules to find the sequence in which operations will be performed in a given expression. First thing. Next, break the entire expression with the help of left and right parentheses in elementary binary expression. You can ask a question, what are the elementary binary expression? Means simply a simple expression involving the binary operator, means a plus b, a minus b, a into b, a divided b. Suppose expression is given a plus b and we want to make a expression tree for expression a plus b. What is the technique? You simply put the operator. What is the operator in this expression? A plus b plus is the operator. Okay, to take the plus operator and make the plus as a root node. Okay, first step. In the next step, make a as a left child and b as the right child. And here you can see the root node is plus and the left child is a and the right child is b. This is the expression tree. This is a binary tree, strictly binary tree. What is the strictly binary tree? Each node has either 0 child or you can say 2 child. Okay. Suppose a minus b. So minus becomes the root of the expression tree. A is the left child and b is the right child. Okay. Suppose expression is a minus b plus c into d. Okay. Now breaks this expression into elementary expression with the help of the left and right parentheses, keeping the operator precedence in your mind. Here we break a minus, we can keep a minus b in left and right parentheses plus c into d into the another right parenthesis, left and right parenthesis. In the place of a minus b, we write the capital A, and place of c into d, you can write a capital B. Now we have changed the entire given expression into an elementary expression a plus b. And suppose the a plus b is given, I have already told you the technique of making expression tree. So make plus as the root node, okay, and make this a left child and b as a right child. This is the one way. Or you can take what is a capital A is a minus b, okay. Now capital A is a minus b is the elementary expression. Therefore take minus as the root node of the expression a minus b. So make minus as a root node and a as the left child of the root node and b as the right child of the root node minus. For b, you can see the expression is the c into d. So star is the root node, c make c as the left child and d as the right child. Okay. So we have made the expression separately for a and capital A and capital B. What will be our next step? To make expression for a plus b, we have the expression for capital A and we have the expression for a capital B. We simply place plus as the root node of a new expression tree, and a, the expression tree for a becomes the left subtree of plus, and the expression tree for b becomes the right subtree of plus. Here you can see. Okay. Let us take the next expression. A plus b divided by c into d minus c. Break this into elementary expression. A plus b, keeping the operator precedence rules and with the help of the left and right parenthesis. So a plus, we can keep b divided by c into one bracket into d minus e in one step. Second step, the result of b divided by c is multiplied by d and we keep this into another left and right brackets. In next step, now we add a to this resulting expression. Okay. Now we keep it into the left and right parenthesis and minus e. Okay. So let us start making the expression tree for the elementary expression. Let us take b divided by c. This is the elementary expression. Therefore, take divided operator as the root node, b as the right child and c as the b as the left child and c as the right child. Okay. Next, make a expression tree for b divided by c. As a whole, we have made the expression tree for this. Now take it as a single, you can say the operand into d. Okay. Now take star as the root node of a new expression tree and the already existing expression tree for b divided by c, and make the expression tree for b divided by c as the left subtree of a new expression tree. Okay, and make d as the right child of the new expression tree. Now we have made the expression tree for b divided by c into d. Next step, we want to make the expression tree for a plus and the new expression tree. How will we make? Take plus as the new root node of a new expression. A, make a as the left child and the existing expression, latest existing expression at the right subtree of the new expression tree. Here you can see in this figure. Okay. In the next step, we want to subtract E from this expression. Okay. Take minus as the new root node and the right child is E, and the left subtree of this new expression tree is the old expression tree. So this way we can make the expression tree for a given expressions. Okay. Next topic, how to make a binary tree from a given general tree. A general tree, you should keep in your mind, a general tree is converted into binary tree and not a binary search tree. We can convert a general tree into a binary tree, but not in a binary search tree. Okay. What is the technique? What is the algorithm to convert a general tree into a binary tree? Rule first is the root of the binary tree is same as the root of the general tree. Rule first. Second, left child of node in a binary tree is same as the leftmost child in a general tree. Rule number 3, right child of a node in a binary tree is same as the right sibling of the node in the general tree. With the help of these 3 rules, we can make a binary tree from a given general tree. Okay. Let us take this is a general tree. Okay. You can say this is not a binary tree. Why? Here you can see that the node C has 3 children, F, G, S. Therefore, it is not a binary tree. And now we are interested to convert this general tree into a binary tree. What is the first step? Root of a general tree will be also the root of the binary tree. And what is the root of the general tree? A. Okay. Now we take A as also the root of the binary tree. Okay. Next step. The left child of root A of a binary tree will be the leftmost child of the root A of a general tree. Let us see. Leftmost child of A, you can see, is the B. Therefore, we will make B as the left child of the binary tree. Here you can see in the figure. Okay. Okay. Now, next step. The right child of A in a binary tree will be the right sibling of node A in the general tree. What is the sibling of node A in the general tree? We can say there will be no right child of A in binary tree since there is no sibling of A in general tree. Why? Because A is the root node and root node does not have any sibling. Why? Because as we already know, root node does not have any parent. Okay. It means that here there will be no right child of the binary tree. Okay. Next step. Left child of B in a binary tree will be the leftmost child of B in the general tree. Let us see. Leftmost child of B in the general tree is E. Now we attach E as a left child of B in the binary tree. You can see here. Here you can see. Okay. Next, the right child of B in a binary tree will be the right sibling of node B in a general tree. Let us find out the right sibling of node B. What is the right sibling of node B? We can say the siblings of node B are C and D. But what is the right sibling of node C? Node B is, we can say, C. Why C and D are siblings? Sibling nodes are those nodes that they belong to the same level. You can see B, C, D belong to the same level. Next condition, they also have a same parent. You can say C and D and B have a same parent A. Therefore, C is a sibling of B, right sibling of B. Now this C will become the right child of B in the binary tree. You can see. Now C becomes the right child of B. Next step, left child of C. What will be the left child of C? Will be the leftmost child of C in general tree. Let us find the leftmost child of C in the general tree. You can say F. So now F becomes the left child of C. Left child of C is F. Next, what will be the right child of C in binary tree? So right child of C in a binary tree will be the right sibling of node C in general tree. Let us see. Node C. What is the sibling of node C in the general tree? You can say D. Now make D as the right child of C. Okay. Next, left child of F in binary tree will be the leftmost child of F in general tree. Let us see what is the leftmost child of F in a general tree. You can say null. And the right child is the right sibling of F. And here you can see the right sibling of F is G. So G becomes the right child of F. Here you can see G becomes the right child of F. Now repeat the same process and you will get a binary tree. Okay. Now we have converted a general tree to a binary tree. Okay. In this video, we have discussed what is a binary search tree, operations on binary search tree, what is an expression tree, how will we make expression tree, and how will we convert a general tree to a binary tree. Okay. In next video lecture, we will talk about threaded binary tree and Huffman coding binary tree. Huffman coding using a binary tree. These are the references for further reading. Any questions? Thank you very much.